problem we're trying to solve, it will cost too much money. And I don't think let me be upfront, we're not going to ask for amount of money to solve problem generally, but we'll be trying to demonstrate a couple of showcases how this type of problem can be in principle solved, and that's what we will be proposing. So the general idea is kind of very simple, right? Can we use self-assembly as really manufacturing tool? So first of all, really how it's done today and what is the limits of the current practice. So the answer is simple. There is no 3D nanofabrication technology today, period. So from that point of view, there is no competition. It's easy for us to say, you know, why we are addressing. But let's be serious a little bit. So how it's done today? There are, in principle, two approaches, maybe a little bit more than that, but in generally, either through conventional nanofabrication, which is intrinsically planar type of fabrication. You can create a couple of layers, maybe 10 layers, maybe 50, but that's in principle extremely expensive and limited. Also, the significant limitation of conventional nanolithography approaches, they, again, inherently incapable of dealing with wet chemistry products. Either nanoparticles which we synthesize through the wet chemistry or different biomolecules. The other kind of more recent development is additive manufacturing, which simply doesn't go to the scale. It also has difficulty integrating different types of materials in different components in precise place in a structure. And obviously there is a kind of also well-known for atomic manufacturing molecular beam epitaxy, which is again kind of limited to particular material types and extremely slow. So from other point of view, if we're looking at the bottom-up approaches, there are various approaches which have been even successfully used in semiconductor industry, like for example, deblock copolymers and so on, or colloidal or nanocolloidal system. The main issue, they don't provide really designability. So you can live with the phase which is kind of nature provided you and so on. So that's really the point which we're trying to solve, how we can rationally envision fabrication through programmable assembly, and particularly kind of in 3D. So the idea is more or less, in some sense, what I was presenting yesterday, in lines that we can envision creating different types of models. Those models can incorporate different functional payloads. They might be optically active, magnetically active, biologically active, and so on. And due to the programmability of interactions or through the DNA, one can imagine that one can create different type of structural organization. And that by itself can be for inorganic materials templated in fully inorganic matrices, and that can be processed by conventional nanofabrication technique and so on. So from point of assembly to after that, it's easy to integrate this kind of how it's done. So from this point of view, there is a question of, by doing something like this, we can decouple assembly process from the component. We essentially can use the same platform for very different types of materials as soon as we can place them inside of the cages. And so the question about encoding of components by decorating them with DNA and creating cages is something which is kind of well known for this community. I don't need to discuss much. So what is really important is how we're transitioning from this idea to practical realization, what is possible to do. So this is kind of a list of certain, I mean, I look at this as a scientific project rather than technological project, and this is type of objective which I think would be very interesting to understand. Really, we're not really focusing on building structure for the structure. I think the whole idea to have functional device in mind, transitioning this to, from inverse design point of view, what structural implementation can be, what degree of tolerance I can afford in order not to kill my function for the structural imperfection to be. And so what degree of encoding I need to incorporate in these materials with understanding that I need redundancy as much as possible to improve my assembly process. How from this kind of equilibrium, a semi-equilibrium picture, I'm transitioning to the pathway and I direct this, and this is where high throughput methodology can be very useful, combined with machine learning and so on. But all this essentially establishing this workflow for this. So let me be a little bit more concrete. And so we have in mind two absolutely different examples, and so depending on a potential funding, we can do them in parallel or select one. One of them is focused on optically active materials, and there are different types of which has been discussed kind of from material point of view for decades, like negative refraction index materials, metamaterials of different kinds, optical computing, and so on. Materials for quantum optics and so on. In many cases, it's a kind of a bottleneck of fabrication. This is just relatively simple example when one can imagine directing the light of quantum dots through the particular type of structure which is shown here. It's a ray. It's two-dimensional in this case, where you have line of quantum dots, you have a line of plasmonic particles, and so they essentially act as a reflector, and another plasmonic particles in front, they're acting as a concentrator. So I'm using this as a two-dimensional example just for the simplicity of the presentation, but having three-dimensional would be control also, for example, polarization and so on. So this is kind of what is shown on the right side. One can encode those components and in principle build this type of structure if we can figure out all these kind of requirements. The other example is very, very different. So it's a kind of cell-free synthesis if we can organize complicated cascades which require 5 different enzymes in the particular kind of nanoreactor, which is essentially nanofluidics. And so all these models can contain different types of enzyme. Again, through the programmability of models between each other, we can essentially organize them in a channel. And this particular implementation here is target synthesis of oligosaccharides, which can be quite helpful from kind of medical perspective, and they're extremely, extremely expensive. So, but ability really not to form one channel, but organize, for example, this in 3D essentially allows to create this kind of active porous media with enzymatic activity inside to facilitate synthesis. So, strictly speaking, we're thinking about organizing the project in general. So we have functional design requirements. There is a certain kind of computational work which needs to be done from functional point of view and translating to structural, again, with understanding the, what level of imperfection one can tolerate, and this is the feedback need to be done in order to do. Then the structural functional design goes to this autonomous synthesis, where we have all this kind of building blocks, which are essentially models, can be assembled in a different way what is needed. So there is a whole kind of high throughput assembly line for fabrication, and then is coupled to the high throughput characterization, and based on combined kind of with machine learning and everything which you can read here. I don't have time to discuss it, but you can imagine we can feed it back to the kind of design parameters. And so this is just kind of a workflow, and the whole proposal is established for some case examples with the idea kind of generalize it to different types of materials and system later. So so the midterm is kind of creating some prototypes of the structure, for example, optically active. And the second goal is establishing this high throughput platform. And so in stage 1, we envision it's approximately $1 million per year. And for 3 years, there are risks, but we look risk as an opportunity. So risk 1 is opportunity to understand really what's the limitation. And so this can inform us about the design. The risk 2 in understand robustness and functional performance. Again, it's going to inform us about what we need to change in the design and the workflow. And stage 2 is unlimited in funding and expanding to other use cases. Thank you.
That you can get.
I'm sorry. Can you repeat, please?
Sorry? Oh, so how are you planning to do the self-assembly? Have you thought about the power of flow chemistry and doing this under flow conditions?
Yes, I didn't discuss all the details. We have actually now have been exploring different ways. Some of them really fully equilibrium, which is required, let's say, certain kind of temperature profile, but also using microfluidics. And and I don't know if I had somewhere, I think I had it because I was saying both equilibrium, non-equilibrium will be used in kind of in this high throughput, this is where kind of, yeah.
So then, like in terms of, so you're making oligosaccharides, and there's like a lot of good photonics tooling for this, such as flow cytometry, and then also cryo-FLM. So why are you using X-ray scattering and electron microscopy instead of like more of these like specific photonic tools that are already focused for like omics-like and glycan-like interactions?
So the tools which was written is kind of more optimized what is presented for inorganic materials. So I didn't discuss all the tools which will be required, for example, for polysaccharides are very, very different. We will require NMR and so on. That's not really was captured. So I just wanted to present it that the diversity of application which can be, but if I would choose, I would probably would focus on the optical first.
All right, wonderful. Thank you, guys.